Assalamualaikum dan salam sejahtera. My name is Nolaila binti Asyari and I from Polytechnic Tuanku Syed Sirajuddin, Brushless. Now I would like to present about the design brushless DC motor for high-speed blender machine using finite element method FEM for industrial application. Blender machine for chili paste. In chili paste industrial application, high-speed blender machine are commonly used for grinding the raw solid ingredient. For design the blender for grinding the food materials, the speed and torque of the machines are very important. Most industrial blender motors use universal motor and induction motor. Many industrial blender use with the induction motor and universal motor because it takes very high current at the start can cause voltage sagging. Universal motor having commutator brush assembly cause sparkling and increased chance of maintenance results in reduction of lifespan. Why BLDC motor used in this study? Because it considered due to the high speed performance suitable for the high speed application 10,000 rpm to 30,000 rpm, capable of give the easy speed torque control required for blender. Most of BLDC motor used for small application which is home appliance, widely used in the high-speed blender machine instead of brush motors due to the high efficiency and good performance. Various experiments were carried out on a commercially available mixer grinder for household application. This is the objective of the study. To design 30,000 rpm BLDC motor for industrial blender machine using finite element method FEM, and then to analyze the effect of motor sizing parameter towards torque and speed of the design BLDC motor, to evaluate the best model for BLDC motor for high-speed blender machine to industrial application. So this is the flowchart for overall methodology to design the motor. In this study, they have 6 design of motor according to the 2 sizes of permanent magnet, and each size have 3 type number of coil as shown in table 3.1. Figure 3.3, the measurement shows the measurement of motor structure design. Figure 3.2a shows the front view of the motor design. Figure 3.2b shows the side view of motor design. Table 3.2 shows the BLDC motor fixed parameters with specification design, while table 3.2 shows the BLDC motor variable parameter specification design. Computer-aided design is used to design every single part of structural motor such as stator, rotor, permanent magnet, coil before assembled as a motor geometry. To operate the motor and analyze all the model, finite element method is used in this study. In this simulation, the effect of flood leakage was observed for all models with a zero input current condition. Figure 4.1 shows the 3-phase sinusoidal waveform flood leakage of a motor for a permanent magnet with dimension of 6 × 10 mm and number of coil N is equal to 144. The maximum value of flood leakage observed in figure 4.1 is 0.1344 Weber. The maximum flood leakage for all models is illustrated in graph of figure 4.2. As a result, the size of permanent magnet and the number of coils have an effect on the flood leakage value. The back EMF for all models was observed in this analysis for zero input current. Figure 4.3 shows the motor back EMF at 30,000 RPM for a permanent magnet size of 6 times 10 mm with 36 coil turn. It shows the maximum back EMF achieved in a balanced three-phase sinusoidal waveform at 208.7566 volt. Figure 4.4a and Figure 4.4b record the maximum of the back EMF based on various permanent magnet size, number of coil, and motor speed from Figure 4.3. Figure 4, according to the result, the back EMF increases proportionally to the increase of speed, so the size of magnet and the number of turn can also affect on the back EMF induced on the motor design. The magnetic torque is measured during this process to determine the motor design capabilities. The motor torque average value was measured in the study at a speed of 30,000 RPM, and the current value was adjusted from 0 to 10 ampere. So Figure 4.5a and Figure 4.5b shows the torque value obtained from the motor design simulation with magnetic size of 6 times 10 mm and 4 times 10 mm and an input current of 8 ampere. For each magnetic size, the average torque value for N is equal to 36, N is equal to 64, and N is equal to 144 are measured, and the process is repeated for input current of 2 ampere, 4 ampere, 6 ampere, 8 ampere, and also 10 ampere as shown in Figure 4.6a and 4.6b. So the data obtained show that the torque value increases to the increase of the three factors, which are the value of the permanent magnet, the value of the current, and the number of coils. Figure 4.7 represents the simulation result of the magnetic flux density distribute for a 6 times 10 mm permanent magnet with 144 turns coil and 10 ampere input current. So the highest value of the flux density point is 2.106 Tesla. Figure 4.8a and Figure 4.8b shows the analysis and recording of the highest value of magnetic flux density by all models. So, based on the data obtained from the motor design simulation, the magnetic flux density on the motor stator chosen is determined by the three factors. One, the permanent magnet volume. Second, the number of coil, and the third one is the input current value. This is the result for the motor selection. Based on the evaluation made, the motor design for magnetic size 6 times 10 mm and 4 times 10 mm with the number of coil 144 recorded the highest value in terms of flux leakage, back EMF, magnetic flux density, and also torque. However, the selection for this design is less suitable because it has a relatively large ripple. Similarly, the motor design used the number of coil N is equal to 64. Both designs also have a large ripple. The selection of BLDC motor design with the number of coils N is equal to 36 is suitable to be selected because in addition to achieving the desired torque target, it also has less ripple. Therefore, the BLDC motor design with magnetic size 6 times 10 mm and number of coil N is equal to 36 was chosen because it has advantages in terms of flux leakage, back EMF, magnetic flux density, and torque compared to BLDC motor with magnetic size 4 times 10 mm and number of coil N is equal to 36. So as a conclusion, the different number of turn and permanent magnet size will affect the result of flux leakage, back EMF, and also torque. And then the value of torque and magnetic flux density increases if the value of current increase. The back EMF value varies in direct proportional to the motor's speed. That's all for my presentation. Now, thank you.